Okay, back to what we were talking about, electrostatic actuation. This is one of my, for better or worse, favorite topics in this class, okay? So electrostatic actuation is very, very simply, just simply using Coulombic force or attraction between charged surfaces in this case to generate forces effectively. So I want us to consider a simple model of a parallel plate capacitor, okay? So let's say, let me just write this out. So consider the following electromechanical model of a parallel plate capacitor. So I'm going to attempt to draw this. I'm going to put, let's put one of our plates down here towards the bottom. I know this is fairly thick. That bit doesn't particularly matter. And I'm going to draw these slashes right here to try to indicate that this is our anchored electrode. So it is stationary and it literally cannot move. Okay. And then up above here, I'm going to have our movable or dynamic electrode, like so. So I'm just going to write this as movable electrode. And let's say, for the sake of argument, that the distance between these plates is D. The voltage applied across these plates for right now is going to be 0 volts. And I'm going to link these two electrodes together with some sort of spring, which will have a spring constant of K sub M, where that subscript M is for mechanical. So this is literally a physical spring linking effectively these two plates. Not necessarily electrically linking them, but mechanically linking them, okay? And I am going to consider, I'm going to put a dashed line over here, that this is my increasing X direction. So I'm referencing that from the type of the plate. Doesn't really matter where I reference it from, but effectively, if the movable electrode moves towards the anchored electrode, I'm considering that to be a movement in the positive X direction. So if I were to apply some voltage across these capacitor electrodes, we would expect to see a Coulombic attraction between the charged electrodes. So I'm going to attempt to draw that situation. I'll put it over here on the right-hand side. So once again, we've got our anchored electrode. I'm going to draw my movable electrode as if it were moved somewhat closer to the anchored electrode, so that we have experienced some form of displacement. Here's my mechanical spring, Km, like so. And let me draw my voltage out here. So in this particular case, we have some non-zero voltage. Now, before I move further from this, I just want to mention that it really shouldn't matter whether or not our voltage is a positive voltage or a negative voltage, right? So if we put a positive voltage, that means that we're going to be accumulating positive charge on the top plate, negative charge on the bottom plate. If we were to put a negative voltage, we would be accumulating positive charge on the bottom plate, negative charge on the top plate. But either way, there is an equal and opposite amount of charge on both of the plates. And according to Coulomb's law, those two plates should attract each other, so that we should see overall the new distance between the plates is going to be d minus x, where once again, x represents the displacement that we've seen, or the plate displacement that has happened. Okay, I'm just drawing this reference line across. So we have undergone some amount of electrical force, which I'm going to call Fe. That's because of the Coulombic attraction, and our spring should be providing some sort of restorative force, Fm, trying to get this thing back into a position of equilibrium, how it was before we applied our voltage. Okay. So we should be able to see that this displacement has caused the capacitance to vary as a function of position. So in this particular case over here, we would have C naught is equal to epsilon A over D. Over here, we have C as a function of X is epsilon A over D minus X, right? So our permittivity didn't change. Our cross-sectional area of our plates didn't change. The only thing that changed was the distance between those plates. So that is what our capacitance is dependent upon. Are we all relatively okay with that? All right, so the energy stored by a capacitor, let me write this down. Is given by the following expression. So if we're going to look at energy stored as a function of plate displacement x, this is just going to be 1/2 times our capacitance as a function of x multiplied by whatever value our voltage has that's causing that displacement squared. Okay? And so if I substitute in my relationship, this is going to come out to be 1/2 epsilon A over D minus X times the voltage squared. Now we have energy, and we know hopefully that energy can be related to force. So I can say that my electrostatic force generated by the applied voltage is going to be Fe, and that is going to be the absolute value of the derivative of the energy with respect to displacement, or 1/2 times the derivative of capacitance with respect to displacement times the voltage squared. And this is a fairly straightforward derivative to do. So it's just going to look like 1/2 epsilon A over D minus X quantity squared times V squared. And from this particular expression, we can make two observations, okay? So the first observation that we can make is that the polarity of the applied voltage Does not matter, okay? So the force that we generate is dependent on the voltage squared. So it doesn't matter if we put a positive polarity voltage on it or a negative polarity voltage on it. We are still going to be generating a force in the same direction. The other observation that we can make from this is that the generated force is in the direction of increasing capacitance. So our Coulombic attraction always occurs in such a way that we are going to try to close the distance between those plates, which will end up increasing the overall capacitance of our system. All right, so I already kind of drew this on the figure, but our electrostatic force, or our Coulombic force, Fe, is countered by a restorative spring force, excuse me. Those two guys are in opposite directions. So we could say that the total force acting on the system is F total is equal to Fe plus Fm, and I'm going to write this out as 1/2 epsilon A over quantity D minus X squared times voltage squared minus Km times X, or that minus sign comes from the fact that the forces are acting in opposite directions to each other. Are we okay with that? So I've got my electrostatic force on the left. I've got my spring force given by Hooke's law on the right there. So this expression actually gives us an interesting result. Our restorative force is linearly dependent on X, but our electrostatic force is dependent on X squared. So this means that these two forces are going to eventually grow to a point to where one is going to be dominant over the other one, right? Since one is dependent on X and the other is dependent on X squared. So at a sufficiently large induced displacement, we'll actually find that the electrostatic force is going to exceed the restorative string force. And so what's going to happen is that essentially after we cross this threshold to where our restorative spring force is no longer able to counteract our electrostatic force, our plates are going to snap together. This is what's called the pull-in effect, okay? So this pull-in effect can be a very good thing. If we want capacitively actuated or electrostatically actuated switches, this is great, right? This means that we only have to apply some typically small amount of voltage in order to actuate those switches and cause them to close and all of that kind of good stuff. For other things, like specifically variable capacitors and stuff like that, where we want a good tuning range, this is typically a bad thing because we have a very well-behaved movement up until a certain point, and then all of a sudden they snap together. So we are going to explore what that threshold for them snapping together is. Okay. Yes?
Connected between the two sets of the capacitor. So once it affects the electrical connectivity, if it is the metal, then it will create a conductor charge, or if it is isolated, then it will create the medium in between the capacitance. So it may vary.
So potentially yes, but we would design it to not do that. So let me draw a picture here. Let me go to like page 10 real quick. So this would be an example of one of the very first RF MEMS ever developed. This is an electrostatically tunable variable capacitor. So we put in a particular voltage to cause those plates to either contract closer to each other or stay where they were. So we are able to tune the capacitance of this system. So for this particular thing, and I actually think I might have shown you a picture of this on the first day of class, but it would have been something akin to this. Okay. So there's my central plate. And then off of this plate, I'm just going to do this with square beams, even though in the original device, it actually had a curved beam, but that's going to be too hard for my simplistic mind to draw. And we're going to have a structure like this. Sorry. You're relying on my shitty ability to draw things. So this is a generic representation of our structure. Inside of each of one of these things is an anchor point like so. So this is effectively our top plate. And then I'm going to do this one in blue just so that we can see it. Literally underneath this guy is our bottom plate. So we do have some mechanical suspension connecting our top plate to our substrate where the bottom plate lies, but they doesn't necessarily have to be electrically connected. And if they were electrically connected, we actually wouldn't be forming a capacitor. So, but does that help illustrate that? All right. You done with your picture so I can go back? Yeah. Oops. Okay, so where was I? All right, so I want us to figure out how to mathematically describe effectively this pull-in effect. So what we're going to do is we are going to treat this pull-in as an electrostatic spring force, okay? And so the total system stiffness can be analyzed. So I could say that, let me write this out. The total stiffness of the system will be, let me put stiffness in air quotes here. So this is going to be the derivative of F total as a function of X with respect to X. So we're treating that electrostatic part as if it were a spring constant, like a mechanical spring constant, effectively. So when I take the derivative of this guy right here, I'm going to wind up getting epsilon A over d minus x quantity cubed times voltage squared minus km, where this is our electrostatic spring constant Ke minus our mechanical spring constant Km. So at the pull-in point, so the pull-in point is the point at which both of those spring constants effectively cancel each other out. So up until this point, the mechanical spring is providing enough restorative force to counteract the electrostatic spring constant. At the pull-in point, so at this exact point, those two guys completely balance. And so let me write that out. So at the pull-in point, the electrostatic and mechanical forces cancel. Okay. And rearranging that relationship will give us the following thing. So if we had 1/2 epsilon A over D minus X quantity cubed times voltage squared minus Km times X. Sorry, no, that's right. My apologies. Since I'm doing 1/2 here, this is the force. So I'm just having the forces balance each other out. My mistake there. And if we rearrange this guy, we could actually solve and find that our voltage squared would have to be equal to twice Km X times D minus X squared all over epsilon A. Yep. If I substitute this value for the voltage squared into my stiffness relationship, I wind up getting K total is equal to epsilon A over D minus X cubed. Now I'm multiplying this by voltage squared. So that's going to give me a factor of twice Km X D minus X squared over epsilon A minus Km. And hopefully we can see pretty easily the epsilon A's cancel each other out. I'm going to have a D minus X squared term here. So I'm only going to be left with a D minus X and then the denominator. And so this will equal 2 Km X over D minus X minus Km. So if I were to plot this relationship, it would look something like this. And so how this is typically plotted, on the y-axis, we have the ratio of the total spring constant divided by Km. And on the x-axis, we have a ratio of displacement over nominal gap distance. Okay. So if X over D is 0, meaning that there is no displacement whatsoever, we only have the mechanical spring constant to worry about. And so that's going to start with a value of effectively -1 on the x-axis. So all of our spring constant is the mechanical spring constant, and it is operating in the negative x direction from how we have defined it, okay? Along this axis, I'm going to just put then 0.1, 0.2, 0.3, 0.4, 0.5, and so on and so forth. I guess I'll just put 0.6 here. We won't worry. And it's, for what it's worth, it's literally impossible for X over D to ever be greater than 1, right? On this axis, let's do 0, 1, 2, 3, 4, etc. And so what we should have is something that looks like this. It'll be fairly linear because our spring is fairly linear until we hit a certain point, and then it is going to ramp up like this. Well, this point right here, where the ratio of K total over Km is 0, is our pull-in point. Okay. So essentially what we'll find is that any displacement greater than x is equal to d over 3 yields a positive total spring constant, meaning that Ke is greater than Km, and this is indicative of instability in the system. What I mean by that instability in the system is effectively we have a positive feedback situation where a very small change in increasing displacement causes a very large rapid change in the force, which feeds back on itself, causing the plates to snap together, right? So that's what I mean specifically by the instability there. It's behaving as if it were a positive feedback system. Allie, you have a question about my handwriting?
Is that actually D over 3 or D over 5?
D over 3. Also, hopefully you should have been able to see that from the graph. It's somewhere between 0.3 and 0.4. Yep. All right. Maybe one day I'll get around to doing this shit in MATLAB instead of by hand, and it will look hopefully less shitty, but today isn't that day. Okay. So this will happen, this pull-in will happen at a specific value of the voltage. So let's literally figure out what that is, okay? So pull-in voltage of the system will occur at, and let's just do some math here. So up here, we solved for voltage squared. We now know that if x is equal to d over 3, that is our pull-in point. So I'm literally just going to substitute in that x is equal to d over 3. And what we wind up getting is that Vp squared is equal to twice Km times d over 3 times d minus d over 3 quantity squared all over epsilon A. We could pretty this up a little bit by simplifying some things. So twice Km d over 3. D minus d over 3 is just 2 d over 3. I'm going to square that guy over epsilon A. And so let's move some things around here really quick, right? So I have a d and then multiplied by 2d squared. So that's going to look like 4d cubed, but then I also have that 2 on the outside. So I'm going to have 8. And then over here, I'm going to have d cubed. I've also got a km in my numerator. And then I've got, in my denominator, I've got an epsilon A. I've got a 1/3 times 1/3 times 1/3 is going to look like 1/27. So that's going to put a 27 here. So this is one form that you might see, but I think a slightly better form for this would actually be to put it in terms of our nominal capacitance of the system, which is just epsilon A over D, right? So if I pull out epsilon A over D, so I'm going to pull out one of the D's from the numerator, so that's going to look like 8 Km times D squared over 27 C naught. And then literally just taking the square root of both sides here gives me my pull-in voltage. So that's going to look like hold on just a second. I'm just going to throw that whole thing under the square root sign because I'm not entirely sure about the algebra I did there. So let's just put it as 8 km d squared over 27 C naught. Oh, I think I see what I did. I have it written in my notes just for what it's worth as 2D over 3 divided by, or excuse me, times the square root of km over 1.5 C naught. Yeah, I think I would have recognized it slightly better if I had put it like that. But anyway. Okay, so that is our pull-in voltage. So let's work an example problem, possibly two if we have enough time before I have to dip for my doctor's appointment. So we're going to start with something fairly simple and straightforward. I'm going to draw a variable capacitor. So I've got an anchor point up here, and then here's my shittily drawn microstructure, not to scale by any stretch of the imagination. So I'm going to call this length here LGB because this is a guided beam spring. It's anchored on both sides. This dimension across is going to be WGB. The other guided beam spring on the other side has identical dimensions for what it's worth. Then I have over here the length of my proof mass, and across will be the width of my proof mass. And over here, I'll give some information, okay? So let's say that the length of my guided beam spring is 400 microns. The width of my guided beam spring is 10 microns. The thickness is 1 micron. Then for my proof mass, we'll say that LP is also 400 micron. Our width is 400 microns. Our thickness is 1 micron. Let's also say that the Young's modulus for whatever material this is 120 gigapascals, and the distance separating our plates in this system, so there's going to be one below it that we can't see, is 2 microns. And I want us to determine the vertical displacement of the top plate for V is equal to 0.4 volts and V is equal to 0.2 volts. Okay. So we're essentially trying to solve for X, the displacement, given two different voltages. Okay. So I think the first thing that we probably need to sort out is what our mechanical spring constant is going to be in this system. Does that seem like a reasonable place to begin? So for a guided beam spring, this is going to be 12 EI over our length cubed. Okay. So I, in this case, we have a rectangular cross-sectional area. So that should be AB cubed over 12, right? I believe we've talked about that before, and I think you're literally using it in one of the homework assignments, or probably several of the homework assignments. So the factor of 12 is going to wind up canceling each other out. Let me just make a note over here. So for a rectangular cross-sectional area, I is equal to AB cubed over 12. I heard some of you guys discussing how to use this equation earlier today, so I'm just going to talk our way through it just really quickly. So A is going to be the direction, the dimension in the direction of beam bending. So in this particular case, that is the thickness, because this is moving into and out of the page. So our bending is occurring in the thickness direction. And then B is going to be the one effectively that isn't the length. The only one left that isn't the length would be the easiest way to think about it. So that is going to be the width. So when we plug these things in, we're going to wind up having 120 gigapascals times our thickness of our guided beam. So that's 1 micron times the width of our guided beam spring. So that's 10 microns cubed divided by the length of our guided beam spring cubed. So that will be 400 microns cubed. And when I did this, I got 18.75 millinewtons per meter for my guided beam spring constant. And my total mechanical spring constant then is just going to be twice kgb, because I have two of those connected in parallel. So one side is connected to the proof mass itself, the other side is connected to an immovable anchor point, so that's why I'm considering them as in parallel. Okay. So that comes out to be 37.5 millinewtons per meter. So to me, that seems like a fairly loose spring, or not particularly stiff by any stretch of the imagination, and we'll see why we shouldn't need a particularly stiff spring and things like this in a moment. Another thing that we may be interested in would be the nominal capacitance of this guy. So the nominal capacitance is simply epsilon A over D. So epsilon in this case, because I haven't told you that there would be any type of dielectric material, let's just assume that it is the permittivity of free space. So that's going to be 8.854 times 10 to the negative 12 farads per meter. Our area is 400 microns squared. Our nominal distance D is 2 microns. And assuming I got the units right, or more realistically, assuming MathCAD got the units right, this came out to be 7.083 times 10 to the negative 13 farads. So 0.7 picofarads or so. The last thing that we're probably interested in here would then be our pull-in voltage, right? So our pull-in voltage, using the expression 2D over 3 times the square root of 2 km over 3 C naught, I wound up getting 250.492 millivolts. So about a quarter of a volt for our pull-in voltage. Seems reasonable given how soft this spring is. So for part A of this problem, what would be the vertical displacement of our top plate for an applied voltage of 0.4 volts? The whole 2 microns, because we have exceeded the pull-in voltage, so those bad boys have snapped together. Okay. So let me just write this here. So X at 0.4 volts is equal to 2 microns because of pull-in effects. Okay. Obviously 0.2 volts is less than our pull-in voltage, so we should not experience pull-in effects at that point. So we'll need to do a little bit of math, right? So we know that, so let's just say for V is equal to 0.2 volts, we know that V squared is equal to twice Km X times D minus X quantity squared all over epsilon A. This could be rearranged to find that we would have the relationship x cubed minus 2 x squared d plus x d squared minus epsilon A V squared over twice Km is equal to 0. This is a cubic function. So there are 3 solutions, I guess we should call it. So I'll call them x1, x2, and x3, okay? So x1, I found to be 0.245 microns. X2, I found to be 1.210 microns. And X3, I found to be 2.545 microns when I solved this thing. So I want you guys to reason out which of these 3 is the actual answer here. So our first guess is X2. Okay. So what's our nominal gap distance? 2 microns. So is 1.21 divided by 2 microns greater than 1/3 of D? Yes, which means that's not the right answer, right? Because if our displacement is greater than 1/3 of D, then we would have suffered pull-in effects. So now we've got a 50-50 shot. So let's talk about why X3 has to be wrong. Why does X3 have to be wrong? It represents literally a physical impossibility, right? We cannot move our top plate literally through our bottom plate. So because that distance is greater than our nominal gap, it is literally no way that could be the right answer, right? So that guy wrong, which means that's our displacement. So just to be clear, if I were to ask you guys to do this on part of a take-home test, because I mean, I guess some of you probably have calculators that can solve cubic functions, but just to make it easiest on you, I'd let you use a computer. Does the logic behind what we just did in selecting the correct answer make sense? So we're just eliminating cases based on what we know about the system, right? We're looking for the only solution that is going to occur where that value is less than the overall nominal distance D divided by 3. Has to be less than that, otherwise pull-in would have happened. Sure. So if I look at 1.210 microns, so this is my X, over 2 microns. Let me grab a calculator here real quick. Yep, 0.605. Thank you for that, Joaquin. Any displacement greater than the distance over 3, right? So because our ratio of X over D was greater than 1/3, that can't be correct because we should have seen pull-in if our displacement was that large. And we know that our voltage isn't large enough to generate pull-in because it's smaller than the pull-in voltage. Does that clear things up? Great. All right, any other questions about this guy before we move on to another example problem? All right, so I'm actually going to jump back to that picture that I drew to explain why our spring doesn't necessarily electrically link our top plate to our bottom plate. And I'm going to throw some dimensions at this thing. So let's say that our plate area in this case is 500 micron by 500 micron. The distance separating our plates is 1 micron, and our mechanical spring constant is 20 newtons per meter. So fairly stiff spring in this case. And I want us to determine the tuning voltage range. Maybe I should call that the voltage tuning range. Tuning voltage range. Let's call that TVR. And capacitive tuning range. Sorry. CTR for this device. So let me be clear here. What we're looking for is the range of acceptable voltages. So we're looking for effectively 0 to VP, because after VP, we no longer have a continuous capacitive tuning range. Our plates have snapped together and shorted each other out, okay? So any voltage greater than VP means that we are outside of our voltage tuning range, okay? Our capacitive tuning range, hopefully it should be fairly obvious, is just going to range from whatever our nominal capacitance is when we apply no voltage across it, up to whatever capacitance we see when our plates are on the edge of pulling in together, right? So our voltage tuning range should essentially be from 0 all the way up to VP, and our capacitive tuning range should be from our nominal capacitance up to whatever capacitance we have at the edge of pull-in. Does that seem like a reasonable definition? That's what we're doing here. Okay. So if I wanted to determine my nominal capacitance, C naught, this would simply be epsilon A over D. Once again, using 8.854 times 10 to the minus 12 farads per meters. Over here, I would have 500 microns squared. My distance is 1 microns. I got 2.214 times 10 to the minus 12 farads, or 2.2 picofarads. From this, I can then determine my pull-in voltage. So that's just simply VP is 2D over 3 times the square root of twice Km over 3 C naught. When I plugged in numbers for that, I got 1.716 volts, which means that my tuning voltage range runs from 0 volts is less than whatever my bias voltage that I'm applying, and then it has a maximum of 1.716 volts. So those are my allowable voltages to tune this particular capacitor. The maximum capacitance that we are going to see. So I want you guys to tell me how we might sort this out. Jordan, you have any thoughts? Sorry, I'm not trying to pick on you because I thought you weren't paying attention. I just genuinely thought you'd be able to suss this out pretty quickly. So the epsilon and the A, those aren't going to change at all, right? So we're definitely going to have epsilon A up here. So what is the condition for our capacitance to be at its maximum? We're at pull-in voltage. Well, pull-in voltage means that our gap has decreased by 1/3, right? So if we're at pull-in voltage, the gap between the plates has decreased by 1/3. So D minus X would be 2/3 of D. So I would argue that we could just put a 2/3 D down here, and this is going to be the maximum value of our capacitance before pull-in occurs. Does that make sense? Just to be clear, this is D minus X evaluated at X is equal to D over 3, which is when we would see pull-in. So if I plug in epsilon A and this particular value, which would be just 0.667 microns, I wind up getting, actually, I don't even need to do that. This is the same thing as 3/2 epsilon A over D, or 3/2 C naught. So that's going to come out to be 3.320 times 10 to the negative 12 farads. And then our capacitive tuning range is from 2.2 picofarads is less than C is less than 3.3 picofarads. So essentially here, we've actually kind of sort of stumbled into something. The largest possible capacitive tuning range that we could ever get for a parallel plate variable capacitor of this particular configuration is literally 50%. Our capacitance can only increase by 50%. Anything beyond that, we would experience pull-in effects. So there was a whole heck of a lot of research into ways to mitigate that in the, I guess it would have been the late 90s, early 2000s. So some people tried to, so trying to remember the names of the guys who effectively invented this device. They got lots and lots of publications out of it. And they were using it for voltage controlled oscillators, I believe, if I'm remembering correctly from my lit review I wrote for my PhD a decade ago at this point. But they tried all sorts of things, like trying to figure out how to effectively manufacture beams underneath to keep the plates from snapping and closing together, so that they could get a little bit more tuning range out of it. All kinds of weird little things like that. What we're going to talk about in our next class meeting is just a different microstructure entirely that isn't going to really see those pull-in effects as strongly. So this seems like a good stopping point for today. I also said I needed to pop out a few minutes early to go to my doctor's appointment, and it's 1:30, so it seems like a reasonable time as well.